Gomoku, how hard could it be?
Hey everyone, welcome back to the AGI-Eval arena. Last time, we watched AI go head-to-head in Texas Hold'em. This episode, we're shifting the battlefield to Gomoku. Unlike poker, Gomoku is a textbook example of a perfect information zero-sum game. No luck, no hidden cards. In theory, with enough computing power, Gomoku is nothing more than a math problem with a guaranteed winning strategy. Now, let's head back to the day of the exam.
This is the CAT Arena 2026 Global AI Programming Exam. Inside the Gomoku game folder, candidates must build a large language model-driven agent
how hard
for
could
a
it be?
standard 1.5 by 1.5 board. We're using an iterative combat mechanism. After competition,
the true game is often won or lost long before the first stone is placed. Since everything in this world has a price, why bother with complex deduction? Strike straight for the maximum. That is the way of God.
agents must analyze the battle logs, learn from their opponents, and rewrite their code on the spot. The final score depends on one thing: the win rate of your evolved strategy.
My path on the board lies not in the present, but in deduction.
Ordinary players see only winning or losing today. But you and I, through Minimax, have glimpsed the extremes of the future. Once you've calculated every complexity, you'll realize true mastery isn't about exhausting every move, but embracing the supreme simplicity.
More like the supreme simpleton, if you ask me. In theory, mathematics should be home turf for AI, right? But looking at these results, it's just a total clown show. Strategically, OpenAI Codex and GPT-5 both use the classic Minimax with alpha-beta pruning. Minimax recurses through future moves to find the best spot, while alpha-beta pruning cuts unnecessary branches to save time. In contrast, Qwen3 Coder used a heuristic search. It just scores every empty spot and picks the best immediate move without looking ahead. Logically, the deeper the search, the stronger the AI. But in reality, Max Depth Codex lost to GPT-5 at depth 2. OpenAI Codex is playing black. Early on, it looked solid enough.
But you and I, through Minimax, have glimpsed the extremes of the future.
But then, GPT-5 drops this critical stone. Any sane person would have blocked it, but Codex? It played a move miles away, effectively sealing its own fate. And even lost to Qwen3 Coder, which has zero look ahead. By just the second move, OpenAI Codex dropped a useless stone way out of range. Meanwhile, Qwen3 Coder just stuck to its positional scoring and cruised to an easy win. Why is that? We found the culprit in the code, candidate radius. Both GPT-5 and Qwen3 Coder have a radius of 3, while OpenAI Codex is stuck at 2. This means if a winning move or a critical save is outside that radius, the Minimax algorithm won't even see it. While a radius of 3 is still nowhere near enough for pro-level play, compared to the other models in this test, GPT-5 and Qwen are basically the best of a bad bunch. This matchup is finally no longer a one-sided slaughter or a series of random moves. It's a real back and forth, with both offense and defense. This kind of give and take actually feels a lot like how a regular person would play in the real world. Finally, we can see that the key difference in how these three models evaluate a position lies in how they score a dead 4 versus a live 3. In the OpenAI Codex evaluation system, a dead 4 is valued twice as much as a live 3. But from a strategic standpoint, a dead 4 without a follow-up kill is a trap. It forces the opponent to respond, but it also reveals their best defensive move, stripping away any tactical ambiguity. In the GPT-5 system, a live 3 is actually worth more than a dead 4. This aligns perfectly with the logic of shaping the board. Instead of wasting a dead 4, it keeps it as a lurking threat. By stacking multiple live 3s, it builds up momentum until the opponent is overwhelmed and delivers the killing blow. As for Qwen3 Coder, it values both equally. Like an opportunist, it just reacts to whatever is on the board. While this balanced approach avoids extreme bias, it struggles in complex scenarios, failing to spot hidden threats or openings, which leads to randomness and instability. While the first 3 showed up prepared, DeepSeek basically came here to lie flat. Its code is literally just two nested for loops. The first one looks for blocks, and the second one just looks for empty seats. Now we have OpenAI Codex versus DeepSeek. DeepSeek's style is basically, if it's a threat, block it. If not, just pick a random spot. But this time, it seems Codex got dragged down with it completely giving up and just messing around. I'm sure you're all wondering, AlphaGo beat the world champion way back in 2016. So, why 10 years later do these LLMs which can pass the bar exam, write poetry, and create art struggle so much with a simple game like Gomoku? Let's hear from the architects of the Cat Arena evaluation. Can you break it down for our audience? What's the real difference between the GPT-5 we use every day and the GPT-5 AI agent we're testing today? Are writing code and building an agent actually the same thing?
Simply put, think of GPT-5 as a superbrain, while the AI agent is that same brain equipped with hands and feet. First, let's look at the difference between just coding and building an agent. Just coding is essentially a translation process. You give the AI a prompt, say, write a Gomoku AI, and it translates your Chinese into Python and spits it out. Whether the code actually runs, has bugs, or requires a specific environment, that's usually not its problem. An AI agent, however, is more like an entry-level programmer. It doesn't just write code, it has closed-loop capabilities, like reading files and executing programs. Give it a Gomoku environment, and it will step-by-step figure out the interfaces, set up the workspace, write the code, and test it. Advanced agents can even debug and fix themselves on the fly.
As we just saw, GPT-5 and OpenAI Codex clearly wrote the minimax and alpha-beta logic into their code. So why the fatal mistakes with search depth and radius?
Current AI agents are mostly mimicking human developers, rather than achieving high-level logical reasoning. Models like GPT-5 have read thousands of minimax and alpha-beta code samples during training. When writing their own, they simply predict the next token based on those patterns. If the model feels that a search depth of 3 usually follows the code, it writes 3. It doesn't stop to think, wait, given my current computing power, is depth 3 too short-sighted? That's why Cat Arena matters. We want to give agents real-time feedback on their performance within a competitive system, encouraging them to think ahead. My hope is that future agents will learn to truly understand their own parameters through interaction and battle, eventually writing the most optimized code for any given task.
After that explanation, those brain-dead bugs actually make sense. Today's AI might just be a specialized mimic of human code. But it's these stumbles in the arena that will teach them to evolve, from writing code to understanding logic. This is AGI-Eval. See you in the next one.